So let's just go ahead and start off with your background. Maybe tell us a little bit about yourself.
I'm a second year PhD student advised by Professor Mate Zaharia and Professor Dan Klein at UC Berkeley's Skylab. Prior to coming to Berkeley, I was a research fellow at Microsoft Research India in the AI for code generation team. And prior to that, I was completing my undergrad from IIIT Delhi in India. From my undergrad, I have had an interest in programming languages and how do programs actually execute or how do programming languages work. So I ended up enrolling in Google Summer of Code under the INCF organization, where I worked with the Maxima programming language team to work on building a programming language translator that would translate Maxima, which is a mathematical programming language built in the 1950s, to modern Python. And this project was entirely in Common Lisp, introducing me to things like functional programming. And that was very exciting for me, which led me to want to dive deeper into programming languages research. And I was very fortunate to get an internship uh, at the summer at EPFL program under Professor James Larus's lab, where I was working on implementing a language runtime for this programming language called CAL, which is a data flow programming language. And there, like, I got intrigued by how to make programming runtimes work, and how our programs actually executed on the hardware, because this programming language also needed to be translated to FPGA. So basically, with all of this background in programming languages, I had always had this interest in AI because I was motivated by this pursuit of how can we achieve intelligence. And actually, my interest in programming language was also sort of related to that, in the sense that programming languages let us express logical constructs very easily that can be executed very fast. And there seems to be some sort of connection between these two. So, from an AI side, this is right around 2021 when GitHub made its first Copilot demo, which my understanding is one of the first successful commercial demonstrations of large language models. And that's when I first heard about large language models. And I was very intrigued because all the auto completion or any kind of features that we had in IDEs at that particular point was just this like autocomplete kind of things. And so I was very intrigued by this technology of large language models, which can literally predict sort of what's going on in your mind, what are the next words you're going to type. And so I really wanted to work on something that would extend large language models for code. And I was very fortunate to get this opportunity at Microsoft Research India, where I was advised by Dr. Shriram Rajmani, Dr. Aditya Kanade, and Dr. Shuvendu Lahiri. And the task was basically to understand how do LLMs work for code generation. And again, this is back in 2021-22. LLMs were just sort of like, to my understanding at least, we just were getting like GPT-3 and those kinds of models, and we were just seeing how can auto regression help with these. Copilot was giving better and better demos, and I was really interested in working on how do we improve the quality and correctness of code generated with large language models. So there I ended up working on this project called monitor guided decoding, that basically combined my prior background in programming languages, so all kinds of static analysis tools, with large language model decoding to provide guarantees about the code being generated. This work was at NeurIPS 2023. And subsequent to that, I got interested in like how can we make AI better in general. So a bunch of things like tool calling, interfacing with the environment, retrieval, etc., which has now emerged to become a field called compound AI systems, more popularly now called agents. And for this, I started applying to grad school, and I was very fortunate that Professor Mate and Professor Dan agreed to sort of advise me and came over to Berkeley around August 2024. And I have been really enjoying my time over here over the past like almost 1.5 years now. In this time span, I have mostly worked on like problems related to optimization of compound AI systems and their benchmarking, identifying issues with them, and extending like techniques and state of the art for AI system optimization, basically. So that's a bit of like my research background.
Awesome. Maybe start off with kind of your first project that you're really proud of.
Great. So, I briefly discussed my adventures into, I would say, programming languages, which was like the Google Summer of Code project on building an automated transpiler, and then my EPFL project on building a language runtime for Cal. The first project combining sort of AI and programming languages was this project called Monitor Guided Decoding. One of the so back in 2021, as GPT-3 came out, and between this and sort of Text DaVinci 3, one of the first questions I was interested in is how do we improve the quality and correctness of code generated with large language models? And even before we try to improve something, we really want to measure it first. So I started playing around with these large language models in context of software engineering. And till then, models were already getting very good at um, self-contained coding tasks like the human eval benchmark, where you're given one self-contained problem, like very simple example, but write a Python script to add two numbers, and the task is to write a self-contained function which will do the task provided. And LLMs are already getting very good at these kind of self-contained tasks. But what I was interested in is lots of people want to do software engineering. And software engineering is not about just writing code in a single file. It's about there is a large repository. That repository has lots of individual components. People define classes, various APIs, functions, types. All of those types may have a variety of information, documentation. Functions may take different kinds of arguments. Each of those arguments may have some meaning, and so on. So, given a repository like this, how can we make AI or LLMs generate good quality code for this? So we first started out understanding what the current issues are. We built up this hierarchy of what are the desirable properties that one wants in a code generating assistant. So naturally, the first thing that the code should satisfy is parsability. The generated code should be parsable. Second thing is the code should be compilable. Third is the code should be runnable. That is, it does not error out with like divide by zero or any kind of runtime exceptions. And then the code should be functional, which is it should actually satisfy the requirements that the user has provided. And then we care about things like efficiency, both in terms of computational time and in terms of memory and network and all of those other resources, efficiency in terms of resources. And then finally, we care about safety, vulnerability, like free of vulnerability, and also the ability to prove that the code is actually correct. So we are implementing a safety critical application, and we want a mathematical guarantee that our code is correct. So we sort of identified this hierarchy that any code should first be parsable, compilable, runnable, functional, secure, provable. And this is sort of an increasing hierarchy such that if you don't have a parsable code, you cannot have a compilable code. If you don't have a compilable code, you cannot have a runnable code. So once we built out this sort of hierarchy or identified this hierarchy, the next task was to understand at that point where the LLMs were, where the LLMs of that day are in this sort of hierarchy. And what we found is parsability was almost 100% solved. Compilability was 100% solved for self contained programs, but compilability was a very big challenge for all kinds of software level or repository level tasks. So, if you take like a Java repository and you ask the LLM to write the function of within a particular file, and now this function may actually be making calls outside this file to functions or classes defined outside this particular file. What we found is LLMs really struggle here, especially because they did not have repository level context. They would hallucinate a lot of these external variables, or they would hallucinate function names. For example, let's say the LLM knows that for doing a particular task, it needs to multiply by 2. And there exists a function called mul2, mul2. And the LLM is, however, not aware that this MUL2 is already defined in an external file. What the LLM may end up doing is it does like star2, which is like the standard operator, but that was not the intent here. Or it may make its own function called multiply2, which is actually different from this. And even though the LLM did the right thing, the code fails to compile because this particular function did not exist in the repository. Instead, the function should have been mul2. So what we found is almost 70 to 80% of compilation failures in LLM generated code occurred precisely because of LLMs hallucinating function names, which were semantically equivalent to the right thing to be done at the point, but because the name itself was wrong, the compilation failed. And this was a major bottleneck. So once we had identified this bottleneck, I spent some time working with systems like CodeQL and language servers to build out this data set that we call pragmatic code. The task in pragmatic code is you're given a large repository, and within this repository you have to implement one particular function. You're given all the context of the repository except this one particular function, and to write this function correctly you need to be aware of all of the repository level context. You need to understand what are the types defined in the file. You need to understand how those types behave and what are their constraints. And once you understand that, you will be able to write this code. So this pragmatic code uh, was the benchmark we built. And then I became really interested in trying to address this problem. So here, one of the key insights that we had was humans, whenever they write code, have lots of information available from the repository provided by the ID as you're typing code. Even pre LLMs, like this is almost going back to 2000s, we have had IDs that can tell you that, hey, when you put dot here, the functions that you can call are A, B, and C. Like you can call a getter here, you can call a setter here, and you can maybe call multiply by 2 at this particular point. We have IDs that can already do this. And humans enjoy this level of guidance and they make tremendous use of this. Whenever you hover over a particular symbol name, the ID can display to you that this is the documentation. This is how you call the function mul2. It takes two arguments as input. Those arguments are of type int and so on. All of this information is very nicely packaged by the IDE and displayed to the human exactly in the context where they are writing the code. So the intuition is, can we not extend all of this extremely rich information to the LLMs as tools? And that's what led us to do monitor guided decoding. Now, some background to this is LLMs till now had not really started becoming instruct LLMs, and they were not very good at tool calling directly either. So you couldn't give the LLM the tool and it would call it. So instead, what we ended up building is this technique that we call monitor guided decoding, where we have a language server running in the background. Now, what is a language server? A language server is basically, okay, whenever you go to VS Code or Cursor and you install a Python or C++ extension, what you're telling VS Code is, hey, can you go and install the Python language server so that whenever you next open a Python file, the Python language server can do all of the analysis that is actually required and provide that to you. Now, we require almost the same kinds of analysis across different languages. So, Microsoft built this really powerful protocol that they call the language server protocol, which basically allows language developers like C++, Python, Java developers to provide a common interface through which they can provide language specific features. Like if I want to highlight the documentation for C++, I can call the C++ language server. But if I want to highlight the documentation for Python, I can call the Python language server. And both of them provide the same protocol, because of which I can just swap in, swap out very easily. That is why you're able to install extensions of like C++, Python, etc. on VS Code. So our intuition was that we will build a language server interface with the LLMs. The language server will provide language specific information. So at any point, the LLM is generating code and it hits a dot. The human would have gotten all of the function names available. What we will do is we will detect this dot and we will call this external language server for whichever language the user is coding in, C++, Java, Python, etc. We will get all of the repository level information and then dump that information either in the context window of the LLM, or what we did in monitor guided decoding is we did masking of the next set of tokens. So after hitting dot, if the function names that are available are mul2 and let's say a and b, there are these three function names, then we will mask out all tokens that are not prefixes of mul2 and a or b. So any token that's like a c, d, e, or any token that's not an m will get masked out, and therefore the LLM is forced to choose between one of the tokens that is like M, MU, MUL, or MUL2, and A or B. And between these, whatever the language model's probability distribution says, we follow that. And just with this small augmentation, what we found is we can take a CodeGen 350 million model that can significantly outperform a 175 billion parameter model, which is almost 500 times larger than it in terms of generating compilable and ground truth matching code. If we actually take a model like Santa Coder 1.1 billion, which was one of the good open source models at the point, we can outperform the Text DaVinci 3 by almost 16% in terms of generating compilable code. So, and like the compilation problem was almost solved to an extent with this, because there was almost zero code hallucination in terms of like at least function and variable names happening after this. We also extended this analysis to show that basically if you even if you have like very complex properties in your code, for example, when we use a database in a software, the standard protocol for using a database in software is you should first initialize your DB object, you should connect with the database server, you should authenticate with the database server, you should do a series of reads and writes, and then you should disconnect with the server and recall resources from the object. So this is a very strict protocol that must be followed when you are interacting with a DB application. And if you violate any of these, your application will crash, or it will have bad consequences basically. So even if you have like such a complex protocol, what we found is you can use monitor guided decoding to enforce that whatever code the LLMs write is guaranteed to follow that particular protocol, no matter whether that is making an external function call, whether that is recursing, whether that is looping. Irrespective of all of these rich control flow, we can give a strong guarantee that the LLM generated code will not violate this constraint. So this ended up being a work that both raised the compilability as well as functional correctness, as well as some sort of security guarantees about the code being generated. This is a field called type state programming, and further details are available in the paper. So this was basically my work at Microsoft. We also open sourced a library called Multi LSPy that provides a very simple Python interface that anybody can use in just 3 lines of code, and they can integrate with the language servers that VS Code actually uses. So if you want in Python code to find the documentation at a particular location in your file, and you want the same level of functionality as that is available in VS Code, you can go to multi-LSPy today and you can just give it the repository location and the location of the symbol that you want documentation for, and multi-LSPy will fetch it for you. And of course, this internally uses all of the rich technology that Microsoft VS Code already built out. We have found that several leading open source coding agents today actually use multi-LSPy internally for their sort of code context coverage needs. And also like there is a multi LSPy MCP server available that many people have built integrations for as well. So roughly this was my work at Microsoft. So yeah.
Awesome. Okay, so maybe kind of in a rapid fire, just in the interest of time, do you want to explain a little bit about kind of DSPI, like kind of dspy.grpo and JEPA?
Sure. So, what we found is this work that I did at Microsoft was sort of like we were building a compound AI system. It's not just an LLM being deployed for solving a particular task, but instead the LLM is augmented with software around it, software that interacts with it and controls it in a way. And also, LLMs are augmented with tool calls today. We build retrievers, we build uh, developer defined guardrails. So, the high level point being LLMs are not being used monolithically today. Instead, we are using them as compound AI systems. And this sort of raises the question of how do we optimize a compound AI system. There is a lot of work that has been tremendous amount of work that has been done in optimizing LLMs to be very good at instruction following or making LLMs very good at coding. But when we talk about a system that is built with multiple LLM components, this is where my research lies in. And DSPy is a popular programming framework that lets you build compound AI systems. And then it provides you the necessary framework to build this in a very nice way, following all kinds of software best practices. And once you build it, you can then use existing optimizers for it. So again, like I was interested in how can we extend AI's capabilities in general, and that led me to working on compound AI system optimization. Within this, I the first thing we did was again like we want to measure how good compound AI systems today are and how good their optimizers work. So for this, led by Shangen Tan, I worked on building LangProbe, which is a language programs benchmark, which is basically a bunch of different, a very diverse set of tasks, along with detailed compound AI systems or agents built for those tasks, and we test out how good different optimizers work for each of these. And so this was a benchmark that we built. Once we built the benchmark, the next thing I was interested in is how can we extend existing state of the art optimization techniques. So one, we had prompt optimization techniques. So Mipro was the state of the art at the time, which was already integrated into LangPro. We also wanted to understand how can we extend GRPO, the state of the art or leading reinforcement learning algorithm at the time, to work for compound AI systems. And led by Noah Zeems, Dilara Soilu, and myself, we worked on building MMGRPO, which is an extension of GRPO to compound AI systems. So in compound AI systems, you can have different language models being called with a different context and in a very complicated control loop. It could have recursion. For example, there was a recent work on recursive language models, or you can have if then else branching, you can have looped control flow, and so on. No matter the control flow, what we found with MMGRPO is you're able to take your compound AI system as it is and apply GRPO to it through the system that we built. So Noah was building Arbor, which is the backend that serves this, and me and Dilara worked on building the front end, which is now called the DSPy.grpo front end. So if you have any AI system built with DSPy, you can go and use DSPy.grpo today to run GRPO optimization on top of it. As we worked on this GRPO optimization, and I was parallelly like I have always been very interested in code generation. So I was working with AMD, which on this very interesting problem which they kindly gave to us, which is they had a new hardware device. Which is Ryzen, which is one of the first x86 boards to integrate CPU, GPU, and NPU all on the same board. And we wanted to see how we can sort of write code using LLMs for this particular hardware. Now the problem is that because the device is so new, there is almost no amount of pre-training data available about it publicly, and no LLMs therefore know about it. Therefore, most LLMs struggle out of the box to generate code for this. And the amount of data that they gave us also was very limited because we just got like one PDF file of like 50 pages of PDF, which is the guidebook they use to enroll new developers, about 20 header files, which specifies the programming API for this hardware device, and about 30 reference return expert kernels. This is not enough to do any kind of gradient based learning, which is like supervised fine tuning. Or the other issue that we also faced is that um, running executing any code on this hardware with profiler on would require a lot of time, like several minutes. And this means that we cannot do reinforcement learning, which runs for up to hundreds of thousands of rollouts for improvements, because we are bottlenecked by the rollout itself. We are bottlenecked by how slow or expensive the rollout is. So this led us to discover this class of problems where, one, we are facing low availability of domain specific knowledge resources, preventing us from doing things like SFT. And also we are facing the situation of expensive rollouts where either the LLM based pipeline itself or the evaluation environment is very slow to run. And because of this, you cannot run reinforcement learning. What we also found is, as I was building a pipeline for this, there was a lot of information available in any and every rollout. So the LLM would generate a lot of chain of thought reasoning that I should write the kernel for this AMD hardware in this particular way, and it would generate code. It would make call to the compiler. The compiler will give an error message saying, hey, this particular API that you're talking about does not actually exist here. You should instead be using this other API, or there might be a runtime error. And all of these kinds of errors, all of this information was being lost when you're doing gradient day, because when you're doing grpo, for example, we just take o of one bit of information from a very long running rollout, and all of this rich information that was available during the rollout is sort of not used for learning. So one key insight that I had is we should be operating in text space by which we can reason about this entire trajectory. So if the compiler gives us an error message, we are able to reflect on the behavior and identify what needs to be updated. And so using this, I came up with this technique called GEPA, which would do reflective prompt optimization. So it will reflect on the behavior and it will update its own prompt to improve or sort of address the feedback that was given. And it paired this with like a very nice genetic loop and a Pareto based candidate selection strategy that we found prevented the model from getting stuck on a local optima. So combining this reflection based insight with a genetic loop and the Pareto based candidate selection, we found that this system became extremely sample efficient. In our paper, we were able to find that across a diverse range of tasks, we are able to outperform GRPO in terms of sample efficiency, outperforming it by as much as 20% while using 35 times fewer rollouts. And this became really useful to us in solving this problem for the AMD NPU kernel generation, where we were bottlenecked by the rollouts being very expensive. So we were able to improve an existing agent for writing code on this pipeline by almost 7 times, achieving up to 70% vector kernel utilization, which is also something targeted by human experts as well. So basically, we started working on compound AI system optimization. We first extended GRPO to work for compound AI systems. We found the issue of sample efficiency. And then we had this insight that operating in text space allows GEPA to extract very detailed and nuanced insights about the task you're doing. And it therefore enables the LLM to significantly improve on that task in very few rollouts. GEPA is now available fully as an open source project where it can be integrated into improving any agent that you may have. There is no bar to the frameworks that GEPA operates with. You will be able to just provide one function that JEPA can call with its own prompts, and it should return a score. And just with that, JEPA and it can also additionally return feedback that can be either machine generated like compiler error messages, or it can be human written. For example, many people write feedback for their AI systems on systems. And JEPA will be able to ingest this and significantly improve the agent in production as well. It's already in production deployment by several large enterprises as well as startups, and they are seeing large gains with it. I invite all the viewers to please go and check it out.
Awesome. So beyond DSPy, .grpo, JEPA, monitor guided decoding, there are a few other papers that you've written that are really exciting. Just kind of in the interest of time, do you want to maybe give us like a 30-second to 45-second kind of like pitch on, I think you've worked on, for instance, LangProbe, language programs benchmark. Maybe tell us a little bit about that.
Right. So basically, there were two works actually parallelly. One was LangPro, which is a benchmark for language programs, and the other project was Why Do Multi Agents Fail? Both of these, Why Do Multi Agents Failed, is being led by Melissa Pan and Mert Semery in Skyla. Both of these works, the sort of area that we are trying to explore is trying to understand where sort of agentic or multi-agent systems optimization is today. So in why do multi-agents fail? We built a taxonomy of what are the various failure categories that multi-agents are facing today. So we identified three very broad categories that, if addressed, can significantly improve the quality of the multi-agent system. And with LangPro, we were identifying what are the real-world agents or compound AI systems people are building, and how can the current state of the art optimization techniques work for these systems. And we identified that, like, this was also one of the first studies that actually identified for the first time that compound AI system can actually give you a very significant quality jump. So switching from one simple predict to a compound AI system gives a jump, and then optimizing them gives you another jump. So we find this like cost quality Pareto frontier improvement using compound AI system and optimization in LangPro. And this sort of motivated the problem statement of we should build better optimizers, more sample efficient optimizers, which led to the works of like MMGRPO, which extended GRPO based learning to compound AI systems, and then to GEPA, which is a more sample efficient reflective optimization technique that even outperforms GRPO in this particular context.
Awesome. And then I think another paper that you worked on, maybe ADRS, maybe tell us a little bit about that.
Right. So, broadly with JEPA, what we are seeing is that it's a language models are really, really good text processing engines where, given some context, they are able to hypothesize and act on that hypothesis. Sometimes this act may be in the right direction, sometimes it may not be in the right direction. But what we have found is combining language models with an evolutionary search algorithm like JEPA is extremely powerful for building systems. For example, the NPU kernel example, or we generating CUDA. So there, what you require is you want code that is both correct, and you want code that is very fast to execute. So there is an automated verification loop, but you also and you also have a verifier, so you can actually run unit tests and you can verify how good that code is working. So given such a setup, we are able to use an algorithm like JEPA to basically take this problem verification domain, ask the LLM to write code, get some feedback from the environment, and ask it to refine it. And we combine this with the Pareto based candidate selection and this evolutionary loop. And we see that we can get very large gains in terms of getting more accurate code, like code that's correct, and as well as very fast. We were able to achieve superhuman kernel performance on many kernels in AMD NPU, as well as on CUDA kernel generation, for example. The ADRS project further extends this, and this is being led by Audrey and Shu at Skylab. They are finding that you can basically do a bunch of like very core systems work, like scheduling algorithm generation, scheduling algorithm heuristics, sometimes even chip design, and so on, using this kind of powerful evolutionary algorithm system. So, yeah.
Awesome. And kind of moving forward more broadly, you worked on JEPA, as we kind of talked about. You worked on, DSPy.grpo, and a lot of these other kind of projects that have come out of maybe academia, and are, really large open source projects. Maybe tell us a little bit about kind of the future of maybe what you're interested in working on. You're still pretty early on in your PhD. You're a second year. What are some of the other kind of things you want to work on in the next few years?
Right. As I said, like I'm really intrigued by the ability that LLMs have once they are combined with an evolutionary search algorithm. So I'm very interested in exploring this direction of what are some real world problems, even beyond what we have already explored, that we can solve with this very powerful evolutionary loop. So that's one thing I'm very interested in, and I believe this is very applicable to AI for science tasks, where the text that we are representing in this context window can be a scientific hypothesis, And as long as we have some verifier for the scientific hypothesis, we can ask the LLM to keep updating its hypothesis. And what, who knows, maybe one day we will discover some very meaningful scientific discoveries using such a loop. So I'm very intrigued by this ability of LLMs to do evolutionary search, and I am interested in working on that. One thing we identified with JEPA is that reflecting on a single rollout is extremely insightful, and it can give very large gains. Currently, we are able to express this as prompt updates, which is working great and people are using it in production. But this raises one question, which is, can we now update our learning algorithms from being sample inefficient like GRPO, which just learns of one bit of information from very long running and complex rollouts, to instead learn reflectively in the weight space. We had some initial work in this direction in the MMGRPO paper itself, where we identified that doing one step of prompt optimization followed by RL is strictly better than doing RL alone. And we believe that this is pointing towards a more general learning algorithm that can reflect and use that reflection to update the parameters of the model. And I believe this is a very exciting, interesting research direction that I'm very keen to take, and would love to collaborate in this space as well.
Awesome. And I guess like more broadly, JEPA, as you kind of described, is kind of this like system optimization through kind of reflective text evolution. And kind of the goal is to optimize these sort of different text components. So that could be AI prompts, code, instructions, so on and so forth. I guess more broadly, there's a lot of other aspects of optimization that might be interesting for compound AI systems, right? Like for instance, here we're looking at like prompts or code or instructions. Have you thought about other forms of optimization? Maybe more broadly, like what are some of the other things you're thinking about there?
Right. So this actually ties very well to the project that I have currently, which is what I call optimize anything. So basically, as I was hinting, what I have found is in JEPA search tree, all you have is one sort of text block that is being updated to make some number go up. And now this text block can actually represent a wide variety of things. In the JEPA paper, we use this to update a prompt that is improving the accuracy of the AI system. But in ADRS, we replace this with like system code where you have like an NPU kernel, or you have a CUDA kernel, or you have a bunch of other things, and that significantly improves the performance. One very interesting thing we did is, can we take the entire agent along with its prompts and control flow represented as a DSPy programming, can we evolve that directly? And what we found is, like, we were able to take a simple agent written for Arc AGI benchmark, and which is doing just a single step chain of thought. We asked JEPA to rewrite the code to make it better. And what JEPA ended up discovering is this very sophisticated 6 step agent that first does natural language rule hypothesis induction, takes this natural language rule, and then asks an LLM to write Python code that implements this transformation rule. And then it goes into this very interesting debug and refine loop where the agent is automatically debugging the code that it wrote, checking whether we are hitting all the training examples correctly or not. And if not, it automatically traces this code and updates its own code. And it does this for a number of times till we get the right answer, and then it executes the right answer on the test inputs and returns that. What this shows is that we are entering this age of self-evolving agents, and JEPA is like JEPA style algorithms can be very powerful in augmenting these kind of self-evolving agents as well. So maybe we are also moving towards this field of like compound AI systems evolving themselves to be better suit various needs, like on the one hand satisfy like latency and throughput requirements, but on the other also improve its capability to improve accuracy and so on. So this is, I feel, like another very interesting research direction as well with compound AI systems.
Yeah, awesome. And I guess like even more broadly, there's a lot of kind of different bottlenecks to, I guess maybe current development of compound AI systems. In kind of the RL domain, one of the largest blockers is, verifiers. Even more broadly, one of the largest, problems is also, people work on benchmarks, right? So for instance, we have, really amazing guests, including, the authors of SweBench and a lot of these other benchmarks that have, kind of come on the podcast. But ultimately, you kind of have to identify like, how good is this benchmark and how do you actually know how good a benchmark is at, evaluating what the benchmark is supposed to be evaluating. So there's a lot of these kind of like natural things. There are things with, like training instability. There are things with maybe lack of data poisoning, like security of data. There's a lot of these kind of different, like problems that we're currently dealing with in your area of research, right? These compound AI systems and things like, kind of optimization, like you've done with JEPA, and even more broadly with like DSPy, GRPO. Like, what are kind of the main problems that you've seen as a recurring phase, throughout every project repeatedly from MSR to like, your time at, Berkeley doing your PhD, and like, what do you kind of see as the major bottlenecks that we need to solve?
Right. So, my understanding is that lots of benchmarks need to be targeting real world settings. So, for example, at the time that I started working on this monitor guided decoding project, at that moment, there was no other benchmark that I could find that would emulate this real world software engineering setting that you are working in a large software repository and you want to write code there. And that's what led us to build this benchmark called pragmatic code. Similarly, when we wanted to work on compound AI system optimization, one of the first bottlenecks we faced is there is no benchmark that actually has real world setting compound AI systems. And that's what motivated the Langpuro project, that we wanted to collect what are the ways people are using compound AI systems in the real world and sort of make that setting very clear and repeatable, which is a necessary quality that a benchmark needs to have, so that people can then see that this is what we need to improve upon. And sort of this is what I feel like Swebench got really good. That Swebench has this very natural setting that there is a GitHub issue and people care about solving that GitHub issue. How do we solve it? And that's the question that Swebench posed, that lots of companies have made a lot of progress on, and that is what we are seeing today, because of which we have very successful projects like Cursor and like the other AI coding assistants. So my understanding is that benchmarks need to target real world settings to the extent possible and sort of emulate that and make it a repeatable system. And that's what becomes like a real world benchmark, in my understanding.
Awesome. Okay, well, without further ado, thank you so much for coming on the podcast. Really appreciate it.
Thank you so much for having me here again.